paper is Adversarial Self-Supervised Contrastive Learning. It's a recent paper that was published last year in NeurIPS. It'll be presented by me, Thomas Cummings, and Lindsay Erickson, sorry about that, and Tushar Sangam and Sunil Kumar Patro. So in this presentation, we're going to go over the introduction, related work, go on to robust contrastive learning, results, conclusion, and finally points for and against the paper. So this paper, it deals with training without class labels. So this can be done using a pretext task that applies an image transformation to the training data. Normally we train a network to output class labels, but since the training data is unlabeled, we can't have the network output the class labels directly. So instead we train the network to create image representations. An image representation is a small vector that contains semantic information about the input image. And so this representation can then be used in an application or downstream task. And in this paper, we're concerned with creating representations that are robust against adversarial images. So we're going to see the trades algorithm compared in the results section. Trades examines the trade-off between accuracy and robustness. Robust error is the error on adversarial images and is made up of two components, the natural error and the boundary error. Natural error is the error on natural images in the training data, and boundary error has to do with how far the decision boundary is from those training samples. So trades minimizes both the natural error and the boundary error during adversarial training. So in this image, we see the class boundary after training on natural images. The yellow and the black dots are training samples, and the black box around the samples is the L-infinity box. And we can see this class boundary passes through the L-infinity box here. So this training sample has a higher boundary error. In this image on the right, the trades algorithm pushes the boundary away from training samples. So this orange dashed line is the class boundary from this image here on the left. And so we can see that this new class boundary no longer passes through any of the L-infinity boxes. This reduces the boundary error and increases network robustness. So next we're going to talk about self-supervised learning. Self-supervised learning uses the training data to create its own labels to train on unlabeled data sets. This is done using a pretext task that transforms the training data and creates the label. So a training sample is transformed using some transformation, such as cropping, flipping, or resizing. And then a pretext task is used to train the network to create the image representations. So for a predictive task, a transformed image is passed through the network to create a representation. And the network learns to create representations that are useful to predict some property of the transformation T. In a contrastive task, the representation for two views of the same image are compared. So the network learns to create the same representation for both the original image and the transform image. The pretext task, it trains the network to learn a semantically meaningful representation of the input image that can be used in a downstream task. A downstream task is some application that uses the part of the network that creates the representation. So the network should be trained using a pretext task that matches the goals of the downstream task. So here's an example of a pretext task from the paper on RotationNet. This pretext task creates image representations that contain information about the rotation of an image. So here we have an unlabeled image X, and it is transformed in one of four ways. It's rotated 0 degrees, 90 degrees, 180 degrees, or 270 degrees. And for training, the labels 0, 1, 2, and 3 are used for the different amounts of rotation. So the transformed image is passed through the network, and the amount of the rotation is used as the training label. And the network creates image representations that are used to predict the amount of rotation for that image. So this pretext task, it doesn't train the network to output the class of bird for this image, but instead the intermediate layers and the output image representation can then be used in downstream tasks. So this particular pretext task is useful for downstream tasks where rotation of the input image might be important. So the goal of self-supervised learning is to use a pre-trained model in the downstream task. So here are the steps to pre-train and utilize a model. So first, you train the model using the pretext task. After training, the CNN has learned to create image representations. Depending on the pretext task, some fully connected layers or projection head may be used by the pretext task. This projection head is specific to the pretext task and can be discarded after training. Next, the weights are transferred to the downstream task, but only the purple CNN weights. And finally, a new projection head is added to the network and fine-tuned for the downstream task. This fine-tuning is done using a labeled data set that's specific to the downstream task. And now I'm going to pass control over to Sunil, who's going to talk more about contrastive learning.
Thanks, Thomas. So what is contrastive learning? So contrastive learning is a technique through which a machine can learn to distinguish between the similar and dissimilar things. It looks at the pair of data points that are similar and different in order to learn the high-level features about the data. So here we can see an image. For each image in our data set, we perform two augmentation combination. That is, this can be the cropped image and this can be the resized, or this can be the resized one and this can be the recolor. We can do any combination of it. So main goal is to make our model to learn that these two images are similar, which is actually different version of the same image. To do so, we feed these two images into our deep learning model, that is f of function. So this can be a ResNet 18 or ResNet 50 to create a vector representation of each image. The goal is to maximize the similarity of the two vector representation by minimizing the contrastive loss function, so that the transformation of the same image should have the similar representation, and the transformation of different images should have different representation. So SimCLR. So it is a simple framework for contrastive learning of visual representation. Suppose we have a training corpus of a million of unlabeled images. So for each image in a batch, a random transformation function is applied to get a pair of two images. Each augmented images then in a pair is passed through an encoder to get an image representation, and this can be a ResNet 50 architecture also. Then this HI and HJ, the representation of the two augmented images, are then passed through a series of nonlinear layers to apply nonlinear transformation and project it into a representation of ZI and ZJ. And then we'll be calculating the, and then we have to maximize the similarity. So here, basically the base encoder is represented by function f, and this projection head is represented by the g function. So now to maximize the similarity between these two representation Zi and Zj for the same image, we need to go through the two steps. The first one is the calculation of the cosine similarity, and the second one is the calculating the loss. So for calculating the cosine similarity, basically what we do is we do the similarity check between the two augmented version of an image using the cosine similarity. So this is the formula for cosine similarity, and where T, this T is the adjustable temperature parameter, which is basically used to scale the input and widen the range of the cosine similarity, and these are the norm vectors. So now to calculate the loss, each augmented pair in batch are taken one by one, and then we can apply the softmax function to compute the probability of these two augmented images that are similar. Notice that the denominator is the sum of epsilon to the power similarity of all the pairs, including the negative pairs, whereas negative pairs are obtained by creating the pairs between our augmented images and all of other images in our batch. And at last, we wrap this value in a minus log function so that we can minimize this loss function. So now in this paper, the author has introduced an simple effective approach to adversarially train a self-supervised learning model using unlabeled data, and it is termed as ROCL, which is nothing but a robust contrastive learning. So basically, it is similar to SimCLR. It just add adversarial training to it. So to do this, it just add additional adversarial image transformation. We can see here that the T of X and T dash of X are the two random transformation of an image, and with which was used in SimCLR version. But now we are having one additional one, that is T of X, that is adversarial image, which is created using PGD attack on contrastive loss. So to get this T of X adversarial, this is the formula that the author has used. So it is somewhat a similar type of PGD version. So we all are familiar with the PGD attack generation. So it is a similar concept. Just here, we are finding the gradient with respect to the contrastive loss. So this contrastive loss has been calculated by this formula, where X is the original image, and X pose denotes the T of X positive set from same original sample X, whereas X negative denotes the T of X negative set as a set of all other pairs that contains other instances of X dash. And whereas Z pose and Z negative are the 128 dimensions that we will be getting, and those represent the 128 dimensional latent representation that we get from that we get as a result after encoding and projector respectively, after passing through the encoder and projection head respectively. So here, basically, instead of the two transformation images, one additional adversarial image is passed through the encoder to get the image representation. The representation are in HI, HJ, and HK, which are then passed through the projection layer, which gives the 128 dimensional latent representation, where we maximize the agreement by considering the contrastive loss. So this is T of X is the augmented image that I already said. T dash of X is the other form of the augmented image. T of X adversarial is the adversarial image of T dash of X. Okay, so this is the overall ROCL framework. But the one thing that we can note here is that the adversarial image is being added to the positive set of Z. So the whole contrastive loss that we have seen in the previous slide can be rewritten as this thing. So here the only difference is that the ZPOS is being added with this adversarial image to it. Okay. So now in the next slide, in this slide, we'll be seeing the algorithm of the ROCL framework, where we take input as a data set D, parameter of model theta, model F, parameter of projected pi, projected P, and constant lambda. So for each training iteration and for each mini batch, we generate adversarial examples from the transformed input by its formula, which is nothing but an instance-wise attack. And after calculating all the generated adversarial images, we'll be calculating the loss of that. We'll be calculating the constructive loss per batch. So we'll go through to calculate that, we'll go through each image of the batch and we'll calculate the contrastive loss with added adversarial loss plus the contrastive loss that doesn't have the adversarial image. And this lambda is the hyperparameter which is used to regulate this equation and to calculate the total contrastive loss. And once this total contrastive loss has been calculated, we will use that to optimize the weight parameter. And that's what we'll be continuing for all the iteration. And this is what the whole algorithm of ROCL is. And from here on, Tushar will be taking on the slides. Thank you.
Sunil, can you turn off your screen sharing?
Yeah.
Okay, so far we have seen the pre-training, the robust pre-training, but it will be useless until we teach the neural network how to use those features to output the class probabilities, because ultimately we want the prediction in form of like the class probabilities. So in order to do that, we fit another neural network on top of the feature extractor. So the projection layer that was used in pre-training, we discard that and we replace it with a untrained linear layer. Let's say its parameters are denoted by psi. And in order to train this model, there are two ways. The one is linear evaluation and the other one is fine tuning. They both are like similar in lot of sense, but they just have a minute difference that we'll recap. So for linear evaluation, let me get a pointer. So yeah, so for linear evaluation, we freeze the model parameters and we train the image in a supervised fashion, right? Because in this in this section of the training, we have access to some part of the supervised data set. The some fraction of supervised data set will be like less, like 10% or 1%, but it's still very less as compared to what your not natural supervised data set, natural supervised training would use. So we pass the data X through the freezed encoder to get its image representation. That is then used by linear layer to map this image to its corresponding label using the normal cross entropy loss. That's your linear evaluation, right? And this can be used on the robust pre-trained network also. While the fine tuning is just that we don't fix the encoder parameter, right? So the only difference in fine tuning is that we will also optimize the like model parameters along with the linear layer parameters, right? Doing just the normal linear evaluation gets good results for ROCL, but authors wanted to push this even further. So they proposed the robust linear evaluation of ROCL. The author's point is that we have trained the pre-trained model of the ROCL on the instance-wise adversarial attacks, right? And which is not a good fit for the class-wise adversarial attacks. And to make our model robust to class-wise adversarial attacks, they modify the linear evaluation protocol to make it into their own robust linear evaluation protocol. So just to recap, we have this pre-training stuff, the 3 augmented views, and then one is adversarial, obviously, and then we map them together. After this pre-training is complete, instead of passing the normal image that we passed in the previous slide, we will pass the adversarial image, and this adversarial image is a normal FGS MPGD or like that sort of adversarial. In that fashion, we find this adversarial image because we have access to the class labels. So we would just, so by passing this image, we will obtain its feature representation, and we will train the linear parameter psi to like map the adversarial image to its corresponding label. And in that it can be mathematically expressed like this, where like psi is the parameter of the linear layer and x plus delta is the adversarial image. Here they don't mention the outer minimization loop, it's just the maximization loop that they have mentioned. But we can, but in paper they mention that they do the adversarial training as mentioned in the figure also. So what does this achieve finally? So by doing robust linear evaluation, they claim that they get a higher robust accuracy, but unfortunately it lowers the normal like clean accuracy, right? And and it can be seen in our experiment section. But before that, they further, the authors use something called as transformation smoothing classifier, right, to further boost their results. But in order to understand the transformation smoothing classifier, we need to go over the randomized smoothing classifier. This is a different actually paper, but by Cohen et al, I think. Yeah, but we cover this in brief. We try to cover this in brief, and I just tell you the intuition here. So the goal is to build a robust classifier G of X on top of a base classifier F of X. Right now, F of X is a trained classifier, we assume that, right? And then the first step is to collect Gaussian samples around each data point X, or generate Gaussian noise around each data point X, right? So let's say if this is our data point X, then the different colors represent the different class boundaries, right? Since this is a non-linear classifier, the class boundaries are like interconnected into, interconnected, and these dotted lines are the Gaussian, your Gaussian noise, right? So for each of the Gaussian noise perturbed image, that is X plus its Gaussian noise, we collect the prediction from the trained classifier F of X, right? And and then we take the majority of the vote, that is whatever class gets the majority of the vote will be our final classifier, or will be our final classified class, right? Yeah, final output. So instead of like giving the f of x's output as like the point, instead of estimating at single point, we take the sample of these different points, and we estimate the result based on that. That's also called as Monte Carlo sampling. And by plotting the histogram of the votes, we can get something, a good histogram like this. And authors claim that or they show that mathematically that the difference between the winner class, that is A here, and the other irrelevant class, which or the non-winner class, then the higher the difference between them, higher is the provable robustness of this data point X. So here we are not talking about the robustness of the network, but we are talking about the robustness of the point itself, the data point itself. And I think that this can be seen from our project too also, if you remember, like at least what I we encountered in our project is that the two images were so stubborn that they were not like getting converged to the adversarial image, or they were not changing the prediction of the network, and that we needed to push, we needed to give them a little extra boost of like giving them higher epsilon, or giving them the higher iterations to make them like adversarial. And I believe that those are like your robust points. That is that is to say, in their vicinity, there was like the point was situated so inside the class boundary that we couldn't find an easy way to like adversarially perturb it to make it cross the boundaries, right? And this can be seen intuitively here without like going into mathematics of like randomized smoothing, that for each data point X, we are like looking at each vicinity, and then we are saying that we'll collect all the predictions of it and then decide on that, right? So instead, if you were following the normal procedure, let's say your adversarial image was lying here and you predicted the class as green or B, then your decision would be wrong. But instead, if you use this algorithm, you would consider all the predictions, and if the majority of the votes are for blue class, then you would predict that as a blue class, right? And that therefore this is called as smooth classifier or Monte Carlo sampling style technique. So this is used this is used by the author, and sorry, I forgot to show you the mathematical. Yeah, so this is how it mathematically looks. The x plus delta is just the image plus its noise, and we take whatever is the maximum votes, right? Then this is being used, this concept is being used by the authors to further improve the ROCL results. And in order to do that, the author didn't have to do much, because let's see why. So in ROCL, we are mapping different views of the transformations into a single domain, right? Yeah, or a single place, right? So it's inbuilt, it has a transformation invariance when we are learning in its feature level, right? We sample the transformations T and from the set of capital T, and then map these different views together. And then in order to just apply the randomized smoothing, all they had to do is Monte Carlo sampling by applying different transformations on the data point X, right? And what they saw is that they achieve the higher that gives ROCL a higher clean accuracy, and it has a good trade-off with robust accuracy as well. It's certainly not highest, but it's really good. So this is the what the mathematics looks like. The T of X is the transformation of X data point. The F of T of X is the penultimate layer before the logit calculation, and LC is the logit calculation layer, or the final, you can say, softmax layer. And then we give the maximum votes, right? The Monte Carlo sampling that I just showed, right? Let's see if this works in the experiment section, right? So here we will see the experiments for the transformation smooth classifier on CFAR 10, right? So here it's not written like these ROCL plus transformation smoothing or something. They have written a clean ROCL here, but this table refers to the new version of the paper, so that's not in the version of the paper that in the schedule. So anyway, so it improves its clean accuracy. As we can see, it's 0.40 plus increase. On the black box 80 means the normal PGD attacks. So even on the unseen attacks, it's increasing its robust accuracy by 0.10. And EOT stands for the expectation of transformation attack, which we are not covering in this section. Let's compare the ROCL plus transformation smoothing with other two algorithms, which is trades plus transformation smoothing, and ROCL plus robust linear evaluation, as I explained in the 4 slides, the robust linear evaluation plus the transformation smoothing classifier, right? And we can see the transformation smoothing has really good clean accuracy as compared to other two algorithms. but it has a lower robust accuracy as compared to the robust linear evaluation. And while I would like to get your attention to the robust linear evaluation as well, that it is decreasing its natural accuracy and increasing its robust accuracy, right? So these results are consistent on unseen as well, but in unseen, in fact, it increases its that robust accuracy as well as compared to the ROCL plus robust linear and the transformation smoothing, right? Once we move into the deeper network, the results are consistent. That is, in unseen attack, we are getting highest robust accuracy for ROCL, TINF, and we are getting lower robust accuracies as compared to the robust linear evaluation in L infinity seen attacks, right? The unseen attack stands here for like, since we are training on L infinity attack only, L2 and L1 are like unseen type of attacks. So what are the takeaways we can say? So obviously deepening the network actually accentuates all the results, all the accuracy metrics. Then adding the robust linear evaluation increases the robust accuracy highest, but it lowers your natural accuracy. And if you want a good trade-off, then the transformation smooth classifier is the one to go. So to explain further experiments, I would like to pass on the control to Lindsay.
Okay. Okay, so for the next experiment, they consider white box attacks with self-supervised training type, CFAR10 data, and L infinity norm, and they considered 3 different methods. So they have SimCLR, ROCL, and ROCL plus the robust linear evaluation. And looking at a ResNet 18 network, they show the accuracy on clean images, and you can see SimCLR had the best accuracy among the 3 methods. But when we moved on to attacked images, you can see right here, this is L infinity attack. And the authors considered these as seen attacks because the models were trained with L infinity. So it's already seen attacks like this. But what we can see here is SimCLR did a really poor job on the accuracy of these attacks, while ROCL for both of these methods did much better. Now, looking at unseen attacks, we have an L2 infinity and an L1 infinity. And what we see here is, again, SimCLR had the worst performance on it, but ROCL had the best performance among L1 attacks, and ROCL plus the robust linear evaluation had the best performance among these L2 attacks. So replicating this into a ResNet 50, again, SimCLR had the best performance or the best accuracy on clean images, but in this case, ROCL had the best performance among unseen attacks, while ROCL plus the robust linear evaluation had the best performance among the seen attacks. So some key takeaways. ROCL has a much higher robust accuracy than SimCLR. Unseen attacks have a higher accuracy than seen attacks. So in both cases, all these accuracies in the unseen are higher than the seen. And ROCL accuracy increases as the depth of the network increases. So what I mean by this is the ResNet 18 accuracies along here, they're lower than the accuracies in the ResNet 50. So the next experiment were white box attacks with self-supervised with fine-tuning training, CFAR10 data, and L infinity norm. Here they considered 4 different methods. They have the ROT pre-trained, ROCL plus supervised adversarial training, ROCL plus trades, and ROCL plus the supervised adversarial training and self-supervised loss. Again, they're looking at a ResNet 18. And the accuracies on the clean images, here you can see this ROCL plus AT plus SS had the highest accuracy. And looking at the adversarial scenes, again, this is L infinity, you can see again that ROCL plus AT plus SS had the highest accuracy. And looking at unseen attacks, this ROCL, this bottom row, they had the highest accuracy for most of the unseen attacks. But when we look at the ResNet 50 network, you can see this ROCL plus AT, they have the highest accuracy on most of the unseen attacks, while this bottom line had only the highest accuracy on this one seen attack and this one unseen attack. So some takeaways here. ROCL plus AT plus SS had high accuracy on clean images and perturbed images when considering a shallow network. So that's when considering this ResNet 18 right here, this bottom row. Accuracy on the clean images decreased on a deeper network. So the accuracies here on the clean images, they all decreased over here. The next experiment, they considered black box attacks on CFAR10 data in a ResNet 18 L-infinity network. So what we have here in the columns, these are the black box models used to generate adversarial examples. So this first column is the supervised adversarial training. Then there's the trades. Then there's the ROCL that generates PGD attacks with the linear layer, and ROCL that generates instant-wise attacks with the projector. So what we see here, we have a epsilon of 8/255. But what we see here is ROCL does a better job than trades against this AT black box attack. And AT did better on the trades attack in this instance, but ROCL wasn't far behind. And what you can see here for this ROCL, the instance-wise attacks, the accuracy is a lot lower than these other accuracies. And the authors claim here that the ROCL had a strong attack on the AT and the trades model. And they replicated this again using a 16/255 epsilon. And again, you can see that ROCL was better than trades on the AT black box attack. And it was similar to AT on the trades attack. So some takeaways here. ROCL had the best performance against AT black box attacks, and ROCL had strong attacks on AT and trades. Next, they did an experiment for transfer learning. So here what they did, they have a source that's the trained linear layer and a target that's the frozen encoder. So for this experiment, they trained the linear layer using CFAR100 data on top of the frozen encoder that was trained with the CFAR10 data. They considered two different methods. This transfer plus method used a wide residual network, and then ROCL that used a ResNet 18. And they have the accuracy for the clean images, and you can see ROCL had better accuracy than transfer. And then also with attacked images, ROCL had better accuracy than transfer plus. Now they flipped this experiment and they did the trained linear layer using the CFAR10 data on top of the frozen encoder that was trained with CFAR100 data. And again, you can see ROCL did better or had a better accuracy in both instances than the transfer plus. So some takeaways here is ROCL had better performance than transfer plus in both experiments. And CFAR100 to CFAR10 had better results than CFAR10 to CFAR100. So here you can see the accuracy on this experiment. All these accuracies are higher than this second experiment. So next they do some ablation studies, and the first one is attack the target image. So here they do instant-wise attacks targeting the original image and also the transformed instances using CFAR10 data and on a ResNet 18 network. So the accuracy on the clean images, both of them are pretty good, but you can see the original image had better accuracy at about 88%. And when you look at perturbed images, we have epsilons of 8 and 16, and you can see the performance between the two instances are pretty similar to each other. So some takeaways here is ROCL achieves high accuracy on clean images for both target examples, and we saw that right in here. The next ablation study, they look at attack iterations on a CFAR10 data and a ResNet 18 network using PGD attacks, and they do iterations of 20, 40 iterations, and 100 iterations. And you can see the accuracy for all these iterations are about 40% for every test there. So a takeaway here is as iterations increase, the performance remains consistent. The next ablation study, they looked at attack loss on CFAR10 data, ResNet 18 network, and a PGD attack. Now they consider these 4 losses. They have contrastive, mean squared error, cosine similarity, and Manhattan distance. So looking at the accuracy of the clean images, you can see MSC had the highest at 88%. But when you look at adversarial images at epsilon of 8 and 16, contrastive learning performed the best on both of them compared to the other methods, which is great because the authors use this contrastive loss to generate instant-wise attacks in their experiments. So the takeaway is that them considering the contrastive loss was the best way to go. Now, they did an ablation study on instant-wise attacks. In this first image, you see a 2D embedding of the adversarial and clean examples in SimCLR. So these blue examples are clean images, and the red examples are adversarial images. And we consider 4 different classes here, and the class is represented by the shape. So you have the X's, the triangles, the circles, and the squares. But what we see are these classes are kind of on top of each other. And also the clean images are lumped together and the adversarial images are lumped together separately. So when we look at this for ROCL, you can see that these classes start to merge together, which is way better. And we also have the adversarial examples with the clean images. So this is a much better representation. So then the authors looked at the black box robustness of a ResNet 18 using CFAR10 data on PGD attacks with different number of iterations. So what they show here is for like an epsilon of 2, one iteration has about a 75% robustness accuracy on this ROCL plus transformation classifier. But when we increase the images to like 10 or 100, we get a higher robust accuracy of over 80%. And you can see that for every single epsilon value here. Then the authors did the ROCL training efficiency on the ResNet 18 and CFAR10 data. So the authors trained ROCL for 1,000 epochs, but this visualization shows that they can achieve the high accuracy on the clean images and the adversarial images at about 500 epochs right here. And they can remain at these high accuracies all the way up to 1,000 iterations, or excuse me, 1,000 epochs. So then I'll pass this over to Tushar.
Thank you. So let's cover the conclusion. So the conclusion is simple. They have trained a robust network with the self-supervised method. They mapped the instance level identity along with adversarial examples, and the transformation smooth classifier can further accentuate these results and achieve a good trade-off between the robustness and the clean accuracy, as well as these results are more consistent with black box attacks, unseen attacks, and transfer learning experiments. So points for the paper are that it achieves a good balance between robustness and accuracy using trades or the TEINF method. Self-supervised, they generate the adversarial samples or instance-wise attack in a self-supervised way. That is, they don't require labels because we don't have access to the labels in self-supervised settings. Then it can be combined with different methods. Once the pre-training has been done for fine-tuning and linear evaluation, we can combine it with different methods. They perform extensive set of experiments, and what I found particularly not good in the paper are that they only consider the CFAR dataset. They only attacked the ResNet model. Then the PGD, when they were doing the ablation study, the PGD attack was limited to 100 iterations. I mean, although the results were consistent till 100th iteration, we did not see the results for like greater than that. While another thing I found interesting is that they use the gradients of the untrained network when they are attacking the instance, when they're producing the instance-wise perturbation, right? The untrained network or the network that is currently being trained, right? Then it's not like a huge improvement over the trades. And so yeah, that concludes our presentation. Thank you.